So I'm going to try my best to start from where most of you probably have questions, but I may not succeed in that because I've been working on portable C++ for a few years now. It may comfort you to know that I learned C++ as I was doing this. So I'm approaching this very much from a Fortran programmer perspective. It might annoy those of you who are experts in C++ potentially who like abstraction, but I'm not a big fan of abstraction unless it's absolutely necessary. Um, so hopefully that shows up in the code that results from using YAKL. But different people have different MOs when they program, and I can respect that. I'm going to share my screen. This is always the magic moment where things tend to break, but hopefully, if you don't see my screen, let me know. Um, I'll start off by saying that you can find this on GitHub/mrnorman/YAKL. I'm probably going to move this to the E3SM repo soon. Because this really, if this is being used by multiple products in E3SM, this doesn't belong in my personal GitHub. So rest assured, it will not remain there. I'm probably going to end up mirroring this from my personal GitHub, and it'll actually reside in E3SM or some other location that it actually belongs in.
We do see your screen.
And you do see
everyone, on the meeting notes, that's the first link if you want to look on your own screen as well.
Yeah, put in 3 links in the meeting notes in the comments down below, or not the comments, but the what actually happened section. One of them is just the GitHub repo itself, the wiki page for the documentation. Another is the API style documentation. If you like this sort of thing, probably most of you don't, but it's more complete. And the other is a publication that just recently came out in International Journal of Parallel Programming, just introducing what YAKL is and why it exists. I'll start off by saying C++ portability libraries are fully C++ with backends that touch vendor languages like CUDA and HIP and SYCL and OpenMP threads. It's not a language extension like OpenACC is, or it's just C++. There's nothing particularly magical happening. One thing that C++ provides that Fortran does not currently is the ability to wrap code as an object that you can pass around. And so the core of portable C++, which we'll get into in a second, is the ability to take a section of code and actually make a class object out of it. Then you can pass that object to the appropriate backend and launch it how you want to. That's why it's called yet another kernel launcher, because that's ultimately all it's doing. You take the kernel, by wrapping some code as an object, you pass it to the appropriate launcher, and it launches it on, say, a GPU or a CPU. So there's nothing particularly fancy going on here. We're just using basic features of the C++ language that have been around since 2011. One of the advantages of C++, if you could see it that way, is that there are a lot of developers for C++ compilers compared to Fortran compilers, so they tend to have fewer bugs, but they do have bugs. So don't let anyone tell you that there are no bugs happening, in especially the NVIDIA backend, but they're far fewer. And from my own experience, OpenACC and OpenMP are a great approach if you don't have any complex data structures, but if you have things like type-bound procedures and classes, my experience has been that it can be kind of difficult to get a truly portable solution on a variety of compilers and hardware with that approach. But there are plenty of cases, for instance, where that may not apply. So let's, now that, just getting out of the way that this is just a library, it's fully in C++, it touches some vendor specific backends, but what you're actually using is just all C++. The same is true for Cocos. The same is true for Raja. So I'll get into some introduction and overview, just kind of going through the documentation. I've tried to document this as well as possible. If you are confused by the documentation or have suggestions for improvements, I'm completely open to that, and I'd love to address your concerns as you're going through it. Let's take a look at some example code. So this would be code that we do in Fortran with OpenACC, for instance. This is probably familiar to those of you who have been in the MPAS world, because Rob and Phil and others have been doing a lot of porting to OpenACC. This is just updating a state tendency based on the divergence of the flux, for instance, in a co-located finite volume method. You have the declaration of the arrays up here. In Fortran, they like to use automatic arrays a lot, although I think the practice in MPAS is a little different than that. If we were to look at the Fortran style code, if you were to port this, we have some declarations up here that would typically be stored away in a header that you wouldn't actually see in your user level code. But let me see if I can get both of these on the same screen. Here we go. So you'll declare the local arrays here, where you have a tend and a flux. Typically, in your code, these would just be parameters that you're passing to the routine, or you're getting out of this this big pointer handler. And when we look at the Fortran style code, the actual code inside the loop looks identical to what you saw previously. We don't need to change the bounds of the arrays from 1 to 0. We don't need to permute the indices from column major to row major. All that is handled by the fact that we're using a YAKL style Fortran array. So this automatically allows lower bounds that are arbitrary but default to 1, and column major ordering, so that the first index is the one that varies the fastest. So you don't have to change most of the code that you're going to have inside the loops. The biggest change, and it's a little painful to get used to, I have to admit, but I've made it as minimal as possible. I don't think we can make the changes less than this, is the looping. So you have a nested set of 4 loops here, 4 do loops. And in this case, I left them commented so we can see what the parallel 4 is actually saying. We always go from outermost to innermost in the ordering when we're declaring what these loops are. So we'll have a set of 4 bounds. We have this nice template parameter. It's the only template parameter you'll likely be using in your user level code, because I think templates are ugly and I try to avoid them in the user level code. But we have the 4 bounds here, and then we're going to pass them to indices that are labeled from outermost to innermost here. We have this nice little YAKL lambda thing. So if you're wondering what in the world is a lambda, this is how we're taking the code inside the loop and creating a class object out of it. That's what a lambda does in C++. Most of your porting will likely be using YAKL lambda to pass this code to the appropriate backend and run it. As you see here, YAKL does support multi-dimensional arrays like you're used to in Fortran, so nothing is going to change in that regard. Another example, if I can find it, from the publication is, suppose we wanted to, say, calculate the maximum stable time step on a grid for a shallow water model, or something like that. This is what the code would look like. You would have the size intrinsics here to find out what the loop bounds are. You would have a huge intrinsic for the original time step so that you can then calculate the minimum time step. You need an epsilon intrinsic to avoid division by 0. And this is what the normal Fortran code would look like. You'll have a collapse 2 of these horizontal looping indices, and you'll have a reduction clause taking the minimum of delta t. If we were to look at what this looks like in portable Fortran style C++, again, we're going to do some declaring of the different types and functions up here, but this will typically be stored away in a header file. This won't typically be in your user level code per se. That's totally up to you as a developer. But when we get down to the actual function, not very much changes. We still have a size intrinsic and an epsilon intrinsic. We don't need the huge intrinsic in this case because of how it's implemented. But we're going to launch a parallel 4 with a label here so that we can do automated profiling and performance analysis of the code. And this is the same for Cocos. I borrowed a lot of the syntax from Cocos. So those of you who've used Cocos before will be familiar with it. It's just the bounds in the Lambda syntax is a little bit simplified compared to Cocos, and Cocos doesn't have the Fortran style behavior, at least they currently don't, that YAKL does. So in this case, the code looks very similar. The only difference is we're going to split this kernel where we're calculating the maximum stable time step for every cell, and then we're going to have a min-val intrinsic that we run at the end. So we're not doing the reduction in the middle of the kernel, we're doing it afterward. So that's the only thing that's changed, but min-val is something all Fortran programmers are familiar with, and if you run min-val on any array, it will launch a kernel for you and calculate a min-val. It will even do so in a manner that is bit for bit the same from one run to the next with the same executable. So this will pass E3SM's restart test. So I want to just, this has been a lot already. I want to stop here and just see, does anybody have any questions or confusions at this point? Again, please interrupt me if you do.
Matt, you mentioned the sort of text in the parallel. I assume that's the same purpose for the text in the different variables. Is that right? Just for profiling or something like that?
Yes, exactly. So when you create a variable, you need to create a label that represents what that variable is. And what that'll do is if you turn on the YAKL debug C preprocessor macro in your flags, if you were to say, suppose you had j+1 here, it'll actually say variable u at, the second index had this bound and it should have been this bound. So it'll turn on automated checking for a lot of things like array bounds for you.
Great, thank you.
Yeah. On that note, that does jog my memory on one thing. This is actually safer than Fortran in a lot of ways. One of the issues with Fortran is when you pass an array to a subroutine and that subroutine provides explicit bounds on the array rather than assumed shape arrays, the compiler, according to the standard, is supposed to trust what you say no matter what. So if you were to put explicit bounds on your subroutine interface that are not actually true to what was passed in, array bounds checking no longer works in Fortran. In portable C++, the attributes of these arrays are always tied to the array itself. So when you pass that array around, you cannot violate the bounds of the array. We don't even let you reshape it to something that has a different number of elements. So one thing that you're guaranteed in portable C++ is you cannot have memory leaks because we handle the use count of a given array and we deallocate it for you just like Fortran does when it goes out of scope. We also do not allow you to change the bounds of these arrays. So it's a lot safer when it comes to array bounds checking than some of the behaviors that Fortran allows. The problem with that is Fortran has this flexibility, which a lot of us rely on. You can flatten an array, you can change the bounds explicitly. It's powerful in terms of what you can do to it, but it's also unsafe. So we're trading some of that nice flexibility for safety. So in Fortran, you can create a pointer that is non-contiguous, for instance. It can be strided in memory. That can do some pretty bad things if you pass it to an array that accepts something that's supposed to be contiguous and declares it so with explicit bounds. YAKL does not allow that. So there are a number of ways that this is far safer than Fortran code, which is odd to say for C++ because we typically associate C code with a lack of safety because of pointers. But one of the beauties of C++ is we hide those pointers from the user, so the user's not allowed to do things like that. So any other questions before I go on?
Can I ask a really simple question?
Please.
Your bounds go from 1 to ny and 1 to nx. What if it was the first one is not 1?
Yes. Okay. So that would look like, you can see the terminal, right?
Correct. Yeah.
Okay. So that would look like YAKL Fortran parallel for bounds. Let's do 2 bounds. You'll use curly braces. So let's say we want to go from -2 to nx plus 1 with a stride of 3. That's what it would look like. So you have lower bound, upper bound, stride. So it follows the same order that Fortran does, and these are both inclusive, just like Fortran.
Okay, that makes sense. Thank you.
Sweet, yep. And that is in the documentation. It's just not in the ones that I showed you there. So that would be showing up under, just to kind of guide you around the documentation. Let me back up. Pressing the wrong keys here. Okay, so we go to the parallel forward bound, C and Fortran style, YAKL inline, YAKL lambda fence. You click on that. We can go to the Fortran style, parallel forward and bounds. That's where you want to go, and it will show you the behavior here with a copy of what the actual do loops are doing. So if you want to see that in the future, this is where you look for that. Okay. Trying to think of the best place to go from here. I don't want to just go word for word through the documentation, because that's something that can be read offline. So let me go through the features that make this useful for Fortran programming. So the first is the fact that we have Fortran intrinsics libraries. And if you want to know a set of what the actual intrinsics libraries are, you can actually go to the code, source, extensions, intrinsics, and these are the currently implemented intrinsics that we have. We have absolute value, the all and any functions from a little bit more modern Fortran. Allocated and associated are the same thing. They're just checking to make sure that the array's been allocated. You can look through here. So there's a number of Fortran intrinsics that we have. We have maxloc and minloc. I will tell you, maxloc and minloc are based on vendor libraries. These are not guaranteed to be bit for bit the same from run to run if you have multiple values with the exact same maximum value. But maxval and minval are. So there are some things that you can use that will give you runtime determinism from run to run, and there are some things that you use that will not give you that. Minloc and maxloc are the only ones I can think of off the top of my head that will not give you runtime determinism to pass a restart test in E3SM. So you can get the shape of an array just like you do in Fortran. So, this can grow as needed, but for the most part, this will probably cover things. There are things like pack, which I have not figured out currently how to do fully on the GPU. So this will actually kick it off to the CPU and do it on the host and then send it back to the GPU, because the problem with pack is we don't know how to send these elements to the correct index in a runtime deterministic manner. And we also don't know the size ahead of time. So there are a number of things that could probably be improved in the future. You just need to let me know as you're running through, hey, we need this function, we need it to run efficiently on the GPU, and we'll allocate some time to implement that. The final thing that is beneficial in Fortran is the pool allocator. So one thing that Fortran code loves to do, here's my nice little snarky graphic of an alligator in a pool. Instead of allocator, that was a speech to text error, so you can thank that for the name of this tool. But Fortran code loves automatic arrays, and they love to create things just kind of on the fly in the middle of a subroutine, which leads to this pattern of very frequent allocation and deallocation of variables. And in that case, it's the problem on the device is allocations are extremely expensive, and so are deallocations because they're blocking. So we want to avoid that, paying that cost over and over again throughout the simulation. So we have a non-blocking pool where we allocate a giant chunk of GPU memory, and this is configurable by the user through environment variables, through runtime variables in YAKL init, and through other means. So you have full control over how this pool behaves, but you'll allocate a giant chunk and then divvy out pieces within that chunk in a non-blocking manner as people ask for it, and it's thread safe, so you can do it for multiple threads. But what this allows you to do is allocate and deallocate very frequently without any penalty whatsoever on the GPU. There's almost zero cost. And any cost there is typically overlapping with existing kernel execution. So you typically don't see anything at all with the pool. That being said, I will say this. When you have bugs in your code, the number one place that you get an error is in the pool. Because typically when you have memory aliasing bugs or race conditions and you're overriding memory you didn't realize, it'll oftentimes lead you to allocate a variable that's just way too large. And that'll show up in an error from the pool allocator. And I'm aware of this. And so I have an entire section of what you do when you come up with an error from the pool allocator. The errors that you get from the pool allocator are extremely verbose and give you a whole lot of information, including the size of the variable you tried to allocate. So if you do run into this error, and you likely will because most codes have, for instance, suppose you try to run a simulation with too few tasks. You just forgot to allocate more tasks for a pretty large simulation, or you put the wrong grid or something like that. It's going to show up in the pool allocator because you're going to try to allocate something too large. So I just wanted to throw that out there ahead of time. I've tried my best to make this as approachable as possible, to describe what a pool allocator is doing and to help guide you through the process of, yes, I've got this error. I have no idea what's going on. Totally understandable. But you can also feel free to reach out if something like that happens. But a lot of times allocation errors are where bugs show up in a simulation. So it would be worthwhile taking a look at the pool allocator page, just ahead of time to be aware of how to handle that error. Let's see.
So what would be helpful to me is to have a better understanding of how YAKL interacts in the multiple settings of CPU versus GPU, and then how it combines with OpenMP and then MPI outside of that.
Okay. So the only OpenMP that happens in YAKL is if you choose to have a CPU threading backend, which will launch your parallel 4s using OpenMP threads. Other than that, there's no OpenMP threading. YAKL does have awareness of MPI. Largely, that is only so that you don't have every single task printing out the exact same message. That's just to keep your terminal output as small as possible, so only the master task is pumping that out. But if you want to see a case of how do we handle both host and GPU code, is that kind of getting to what you're thinking of?
Right. It's running on a GPU that's completely new to me, as well as C++.
Okay.
But so I've gone through the instructions, and I really appreciate the mini weather app, and I've run that, and I've made some alterations to understand it. But when you're running on the GPU, I guess I'm very familiar with running in parallel on CPUs, and everything with the GPUs is new. So anything you could describe with that would be helpful.
Oh, great. Okay, yeah, that helps a lot. So let's go in that direction. There are two things to consider for a GPU that you're probably not used to. The first is that there are two memory spaces now, and this is by far the most painful aspect of running on a GPU. This causes more problems than any other aspect we have. So you have one set of memory. I'm going to CD into miniweather to show this, and take a look in that file. Miniweather MPI parallel4.cpp. So here we go. Again, in the top of the file, I do a bunch of type defines to just declare what these data types are. But that's in the header. That doesn't usually make its way into the user level code. Let's get into what's actually happening. So we're going to have the perform time step that does a very poor Runge-Kutta integration technique. It's not even strong stability preserving. I may change that in the future, but I'm just trying to make this simple for the users who are trying to learn HPC programming. So let's get into where this actually happens. Okay, so here we are. We're going to compute some tendencies. We're going to pass in data. We're going to have local data that's declared kind of like an automatic variable in Fortran. So we have two different random access memory spaces. We have the host and we have the device. And these are completely separate, and you have to move data between the two if you want to run it that way. So let's just talk about this line right here. This is allocating a variable flux with this label flux. It's going to be 3 dimensions, and it's, unfortunately, this is C style, so the fastest variant is going to be nx plus 1 rather than, this isn't Fortran style code. But this is allocating on the GPU. If we look at this real 3D, we try to find where that is declared. This is YAKL memory device. And so this will be declared on the device. There's also a memory host, and this will allocate on the host. And so the GPU can never use data from the host, and the CPU can never use data from the device. There are exceptions to this, but I don't recommend that you try to use them. If you turn on managed memory and you try to use device memory on the host, yes, you can do it. The performance is probably going to be very, very poor because it waits until a kernel hits to migrate that memory back to the GPU. So the latency is insanely high. So while you're developing a GPU port, you can turn on managed memory, but when you're actually trying to run in any sort of performant manner, I highly recommend that you not do that. So let's go into the MPI routine. So when you run MPI, you can, suppose you don't have GPU-aware MPI. That's a different topic altogether. GPU-aware MPI means you can send data directly from a GPU, from one GPU memory to another. Some machines support it, some machines don't. But suppose you have normal MPI that doesn't have GPU-aware implemented. There's this deep copy 2 here. So we'll have an array of the send buffer on the GPU and an array of the send buffer on the CPU. They each have the exact same amount of memory allocated, and I'm just going to deep copy the data from one to another. And this in CUDA would implement a CUDA memcopy device to host, for instance, under the hood. But you'll have one array, and you'll have a deep copy 2 function and another array inside of it, and you're just sending your data to them. So this way, after this deep copy 2 is finished, I can now run it under MPI because it's on the host where it belongs, because GPU-aware MPI will not actually be able to see the host memory, the device memory. So that's the number one thing to think about, in my opinion, if you're new to GPUs, is you have to move data back and forth from the host and device as you need it.
So can I just repeat
Yes.
what you're saying in my words, which are hopefully maybe close to how other people understand it as well. So in the codes that we've traditionally used, like POP and MPAS, we use MPI between CPUs and between nodes in order to communicate the halos. But here, you're using something, and I didn't realize it's still called MPI, but it's GPU-enabled MPI.
Yeah.
But you're actually passing the full array. Is that right?
Well, MPI only takes pointers, right? But the question is that pointer valid in the host memory, or is that pointing to data valid in device memory? So with GPU-aware MPI, you can pass a GPU device memory pointer to the MPI library, and it will move the data to the host and send it off for you. If you don't have GPU-aware MPI, you have to move that data to the host memory yourself first, and then call MPI. Does that clarify?
Right. I think Phil's gonna.
Yeah, I don't know if you're thinking, Mark, that he was actually using MPI between the host and the device, and that's not the case. It's just you're still doing MPI between nodes here. It's just whether you're accessing the GPU memory or the
Oh, memory. Okay. No, so I was mistaken. You are not using these commands to pass from CPU to GPU.
I think bringing up GPU or MPI was a mistake because it's convolving two issues. you should expect to be using deep copy 2 and create host and device copies. So let me just move back to the documentation where it's a little safer in that regard.
Right. So let's say that we're only on one node and we're not passing things between nodes. I guess that the first lesson for all of us new people is, how do you communicate between the CPU and the GPU?
That is using these routines here. So we have a deep copy 2, a create host copy, a create device copy. So if you have an array that's valid on the device and you want to use it on the host, I would use create host copy. And that will take the exact same data, create a host resident memory allocation, and copy the data to the host. And then you can use it on the host. And if you have a host memory variable that you want to use on the device, I would use the opposite. So if I were to have an array, suppose I have a real host 1D var, and let's suppose I want to read it, read from file or something like that, because file IO typically has to be done on the host. Now suppose I want to use it on the device, I would say that's all you have to do. This right here will create a device copy of this host array that you have. It's now valid on the device, and now you can use it inside of Parallel 4. So the rule of thumb is anything inside of Parallel. So the other thing about GPUs is anything you do inside of Parallel 4 is on the device. So Parallel 4 will launch things on the GPU in a completely separate memory space. So Parallel 4 should never try to use data that was created on the host. That's the rule here. So if you're wondering, how do I know what is actually on the device and what's on the host? Anything inside these Parallel 4 functions is run on the device. Everything else is run on the host. So if you're using this variable blah, it had better be allocated for the device. This var should be on the device. That's the rule of thumb there. Does that make sense?
Yes.
Okay. But if I were to have a for loop here, this is on the host, but this is on the device. So this kind of helps keep track of things. So if I were to have this variable blah, which would end up being a real 1D, it's valid on the device. Then if I want to use it here, I would have to then create a host copy, and you're done. Now I can use it inside this for loop here. So this is kind of an example of how you would do that workflow of passing stuff to and from the GPU. Does that help?
Yes. And if it's on the GPU, I can see that you can conduct your calculations within the lambda of the Parallel 4. Is it available? I mean, like, let's say we were just doing something very simple of using some print statements to inquire what those variables are. Can we do that within a Parallel 4? Is it available to us?
It's not portable if you try to do that. So one thing there are two approaches to this. If you use printf, the typical C thing, then you can do it. That's portable. Actually, I wouldn't do it. SYCL has its own weird rules about printf. So if you really want to see directly what's on the device in a portable way, I would just say standard cout blah. So I have implemented these streaming operators to print out arrays both on the device and the host. So if you would do this on a device array, totally fine. I will copy it to the host for you inside of YAKL, and you can print out exactly what the array is. But doing it inside a kernel in a portable manner is kind of tough. Does that make sense?
Yes.
So there are a lot of gotchas here. If you're only using CUDA or HIP, I think you can get away with printf. So you do a %lf for a double, blah, at I, and this will work in CUDA and HIP. I don't think this is going to work in SYCL right now. There's an extension they're trying to add to the compiler to make it work. So you can do this for quick debugging if you want, because you're probably not going to be running on Intel GPUs immediately, but I don't know that this is going to work with Intel, but it should work with CUDA and HIP.
Okay, that helps.
Can you explain, and then I get with the create host copy and create device copy, what's the deep copy then?
Yes. So suppose you already have a copy of it. So let's make a scenario where I've already allocated blah underscore host. So edit blah on host, and I wanted to go back to the device because I'm going to use blah on the device now. You know, new var at I equals blah at I. So suppose I want to read it on the device. This is not allowed. So currently, if I were to edit this variable on the host and then read it on the device, it's not updated on the device. The device doesn't know about it yet. So if I wanted to update the device's copy of this, then I would say blah host.deep copy to blah. And now this is updated before this parallel 4 runs. So I now have an updated copy on the device.
Okay, that makes sense.
Yeah, so it's doing the exact same thing. It's just not allocating a new object beforehand.
Got it.
And I think this is a good time to get into the number 2 reason GPUs are very different. So the number 1 reason GPUs are different is the fact that they have this separate memory address space, which is annoying to have to deal with. But for now, we have to. The second is this parallel 4 happens immediately and immediately returns back to the host. Back to here. So if we were to do this here, I can't remember if this is expected to succeed or not. My gut tells me this is not going to succeed. Actually, no, this probably would succeed, but not. You shouldn't count on it. If you want to do something on the host with this variable, like let's say let's switch this around. So now we have. Suppose we wanted to take a variable on the device and copy it to a variable on the host. This is a bug that I've had happen a number of times, and it's very frustrating. We'll have a for loop, and suppose we just want to find out what it is, for instance. This is going to fail, because this will return immediately to the host and will begin printing out what it is. But the actual copy has not happened. So this is asynchronicity. There are a number of calls that are asynchronous and immediately return to the host. This is required for performance, and this is how CUDA, HIP, and SYCL all behave natively. But it's not something a lot of us are going to be used to. So when you launch this parallel 4, it goes back to the host immediately while it's computing this, so that you can actually do asynchronous work between the device and the host. This is the default behavior. So most of the time it's okay, but there are a few cases like what you see right here highlighted where it's not okay, because it's going to still be copying this while you're printing out the value on the host. And so some of these values are going to be stale and won't actually have the update from the device. What you need to do is put a fence. And this means all previous GPU work, parallel 4 and deep copy 2, have to be done before we go past this on the host. Some of you are used to this sort of behavior with OpenMP, certain flavors of OpenMP. But a lot of you won't be used to this, so I just wanted to make this clear. It goes immediately back to the host. But one thing that it does do, if I have multiple parallel 4s, so suppose I had this sequence here, the ordering of the sequence will be respected on the device. So the device will calculate these things in order, but each of these calls will return immediately to the host before they're completed. So that's just something to keep in mind. If you were to say do file IO, you really need to have a fence before you do the file IO because it wants to know what the updated values are from the device, for instance. Those are the two big things to think about when you're running on a GPU, is the fact that all these parallel 4s that you're launching, they're completely asynchronous with respect to the host code. And if you want to do something that depends on the actions of these functions, you have to put a fence first and then continue your work on the host. Is that clear-ish?
Yes, that part is.
Okay.
I didn't realize that you have to have different variable names between the host and the device. Is that typical?
In C++ portability libraries, yes. In OpenACC, no. So OpenACC will mirror things with the exact same variable name. In C++, all of your identifiers in the code have to have a different label.
I see. So whatever we're running with on the GPUs have to have additional names for all of our variables.
Correct. And most of the time, I mean, eventually the goal is to run most, if not all of the code on the GPU with the exception of MPI data transfers and file IO. In that case, you won't have multiple copies because they'll be on the GPU anyway.
But you still need to do the IO and you need to initialize it, initialize your variables and send it to the GPU, and then at the end do perhaps some kind of analysis, but at least output at the end, right? So you always have to have, you always start and end with your variables on the CPU.
Correct.
I would think often they would have like a generic name if it's IO, right? You wouldn't necessarily have to say temperature and salinity and so on. It would just be whatever sets of variables.
Like a work array sort of thing that you're
exactly like that. Mm-hmm.
And so if you want to know whether something is synchronous or asynchronous, this API documentation tells you. So let's go to the parallel 4, for instance. You'll see this asynchronous tag on the documentation for that. So this tells you, hey, this is going to kick it right back to the host, so just be aware of that. This is not a synchronous call. The same is true for parallel outer. And if we look in the C array or the F array class, this is what we'll be using. Style Fortran right here. If we look in here, these are the only other functions I know of that are going to have the asynchronous tag. Here we go. So an operator equals, if you were to assign it to a single scalar value, for instance, that'll be asynchronous. So this just tells you what's asynchronous and what's not. Turns out create host copy and create device copy are actually not asynchronous. They will wait until the copy is done before returning, because that is what the user would probably expect anyway. So there is some documentation to help you understand whether the call you're doing will kick immediately back to the CPU or not, because some of them do wait. So hopefully that'll help with some of the confusion there. There are debug flags to help you. So if you think you might have messed up in this regard,
So do others on the call have high-level questions of?
Yeah, well, let's go to the high-level questions. Yeah.
Here's one. So you have the Fortran style and the C++ style.
Okay.
If we're making a clean break with Fortran and starting over again, I would have thought we just start with the C++ style and not look back. Do you have thoughts on that?
You're free to do that. This is yours to use, as you feel like your project needs. I will say Fortran style for some codes makes the porting process of existing codes way faster. The RRTMGP code, for instance, I had nearly all of it ported from Fortran to C++ in about a week or week and a half. Because of the Fortran style array, I didn't have to permute everything, which is an error-prone and difficult task to do. Didn't have to change all the indices to -1 because they're 0-based instead of 1-based. So for the act of porting existing Fortran code over, it's quite easy to use. But it's completely up to your project as to what you think is the best approach.
Okay. Phil and Sarat, I'm curious if you had thought about that already. We don't hear you if you're talking.
Yeah, no, I guess so. If we are starting from scratch, then it might make sense to stay with C. But on the other end, like Matt said, if we're porting lots of routines over from Fortran, if people are more comfortable doing that, we can do that initially and then transfer that later. So,
right.
Well, I guess what we can't do is mix the two. So we probably want to decide.
Yeah, so I guess that's a major decision we have to make soon.
And if you were to use the C++ style, with the exception of the pool allocator, you may consider using the Cocos library. It's a little, okay, the build system's a lot more complicated, and there's some things that are more complicated. They don't have a pool allocator, so you'd have to handle that situation. But I wouldn't just reject it out of hand. If you're considering a C++ style, it might, Cocos might be a better choice. It's just something for y'all to think about, I think. But I'm happy to support your project with YAKL. Sarat and I and others are happy to do that.
Matt, I have a question about interoperability to other GPU framework.
Yeah.
Like, for example, if you want to, for some reason, just use some part of the code, want to use OpenMP target or something like that, is it possible and YAKL support that?
To have two different backends in the same executable? Is that what you're saying?
Not really backend, just one part of the code. We just want to use YAKL. But
Okay.
the other part, we just want to, let's say, OpenMP target without YAKL. Is it possible to do that?
It is possible to do that. Let me show you the Fortran hooks. Let's see. We'll have a unit test for Fortran control of YAKL. You can call Gator init, which will start YAKL if it's not already started. It's okay if it's already started. You can still call this. It just won't do anything, and you're totally fine. It'll, allocate the initial pool memory, and then you can actually allocate contiguous pointer variables using YAKL memory in C++. So when you do this, this is available in both C++ and Fortran. You can set your own lower bounds in Fortran if you want for the pointer variable. And then you can deallocate those, which will disassociate the pointer and deallocate it from the YAKL pool, and you can finalize. So you have control over YAKL from Fortran, and you can share memory with YAKL in Fortran. So this, if you were to have a device allocation, then this variable is now valid on the device as a contiguous pointer. You would have to declare it that way in OpenACC and OpenMP target offload. So you have access to the memory from YAKL within Fortran. You also, when you interoperate with YAKL, it's the same as if you wanted to interoperate with Cocos or CUDA or HIP. You have to use those features in OpenACC and OpenMP target offload that allow you to declare something as already a device pointer or to get the actual device pointer from it and there are a few others I can't think of off the top of my head, but that functionality exists in OpenMP target offload. The one other thing I'll mention real quick is if you were to do managed memory in YAKL and you have OpenMP target offload in the same code, I will actually do a target associate pointer to let the OpenMP runtime know this variable is handled by managed memory. It's already on the device. Don't move it yourself. So that's a convenience feature. If you turn on managed memory for a quick porting effort from OpenMP target offload, actually let the runtime know, don't bother moving this. It's already on the device, because the CUDA runtime will handle that transfer for you. So those are the only things I can think of specifically for YAKL. Otherwise, just use the existing functionality as if you're using CUDA. Does that help?
Yeah, definitely. So when you show, yeah, this one. So for example, if we want to use one variable allocated in the YAKL pool, how can I get the name of the variable or pointer that can be used in the other part of the code?
So you'll declare contiguous pointer A here, and you'll say, you want to allocate. What specifically are you asking?
No, I'm just yeah. So when I look at your code, there's A is always allocated. So is it just use that A variable in other part of the code, other part of the GPU code as it is? This is
In the
something.
Fortran code or the C++ code?
I mean, it probably is a C++ code because we are going to use a C++.
Off the top of my head, I don't know. This is going to call Gator allocate C, so we're going to call the Fortran binding. Let's just take a look at. Sorry.
So I think people may need to drop out if they have a meeting at the next
If
hour.
you have another question while I'm looking this up, please ask.
So I think we'll plan for this to be an occasional but ongoing thing. We'll definitely be consulting with Matt. So why don't I'll go ahead and excuse everyone, and thank you so much, Matt. I'm going to stop the recording.
Okay.
And we'll definitely be talking again and sending you our questions.
Sweet. Yeah, please just reach out to me. I'm available.